So we are ready for the final talk of this session. So the next speaker is Claude Duhr, who will tell us about Feynman integrals beyond modular forms. Please, Claude, the stage is yours.
Thank you. And first of all, let me thank the organizers for giving me the opportunity to speak here. I will mostly talk about a recent paper that we posted in the archive last week. Here's the archive number. It's actually related to the talk that Albrecht Klemm gave earlier this week. But there will also be some small input from some upcoming paper with Johannes Brödel and Nils Martes that is in the final stages of the write-up right now, so it should be out in a couple of weeks. So the talk is about Feynman integrals beyond modular forms. Now, what do I mean by that? Well, we're the last day of the conference, so I'm not going to spend too much time on introduction. We have had very good talks on collider phenomenology, by Bernard, and they show that Feynman integrals are very important there. We've also had very nice talks about gravitational waves. They also show that amplitude techniques are important there. So Feynman integrals are the building blocks for many of these calculations, so they are important. We want to understand them. We also know that they have a rich mathematical structure. We have had a nice talk by Stefan Weinzel yesterday, by Francis Brown today, where we've seen how Feynman integrals can actually even teach us something about new mathematics. And so we've also seen talks by Stefan yesterday and by Xi earlier today that the cases of polylogarithms and the elliptic generalizations of Feynman integrals associated with elliptic curves are by now relatively well advanced. So especially, for example, in Xi's talk, they have computed a double box related to an elliptic curve in terms of elliptic generalization of polylogarithms. So that is something that is not at the same stage as normal polylogarithms, but it's well advanced, I would say. But we also know, and it was already mentioned today, that elliptic curves are not yet the end of the story. In particular, we also have examples of Feynman integrals that are related to Calabi-Yau varieties. And there, of course, the situation is very different. So there, the function space, for example, is very poorly understood, just because maybe both the mathematics is less understood than the mathematics of the curves, but also because it's not a topic that is maybe so familiar to people doing particle physics. And so if we want to understand better what kind of mathematical structures we get from Feynman integrals, that's maybe, I would say, the next frontier. And so the goal of this talk is going to be to say, well, let's take the simplest example of higher loop integrals that give rise to Calabi-Yau varieties and show how, if you understand the geometry, we can actually do something with it. In particular, that we can generalize in a very natural way formulas that we know for low loop orders. And this family that I'm going to take is the family of banana integrals. And I will restrict myself for now to two space-time dimensions, just because there the formulas look nice. There's nothing intrinsic about it. And I will comment on dimensional organization or equivalently other space-time dimensions at the very end. So the banana integrals are essentially two-point functions with a bunch of propagators. So for example, one loop is just a bubble. And I assume, for example, that all the propagators have the same mass. That integral is well known. What you get is you get square root as a prefect and algebraic function sitting in front, and then you get an integral over this very same square root. And you can do the integral in closed form, you get a log. So that is something that has been known for 20, 30, 40 years. The variable z here is essentially the only dimensionless quantity I have in this integral, which is the mass square divided by the momentum square p is the momentum flowing into the two-point function. At two loops, this is the integral that Stefan had in his talk yesterday. It's the sunrise integral. And again, I assume all masses equal. And if you remember Stefan's talk yesterday, you've seen that it's associated to an elliptic curve, and the result involves modular forms. So here, my H3 would be a modular form of weight 3. We'll look again at the definition in the next slide, but I also refer you to Stefan's talk yesterday. And outside sits, and said no longer an algebraic free factor like here, but a modular form again. At weight 3, the situation is similar. And so I think this is a very natural place to start investigating what other things you get, because it's known that if you go to higher loops, you get Calabi-Yau varieties. And we will define what they are in a second. I just want to say that you should understand what's coming. So the goal will be to explain what sits here in the general case as kind of, well, when people 5 to 10 years ago started to get interested in the two-loop sunrise to understand how elliptic Feynman integrals look like. So the first place to understand this was to look at the two-point function, the equal Massaras integral. We're going to do the same now, but in the Calabi-Yau case, essentially with an arbitrary number of loops. But you should see this, the extension that people have been doing 5 or 10 years ago in the two case. So just, well, these are the definitions of what Stefan had yesterday. The modular form is essentially a holomorphic function on the upper half plane that has a very nice transformation behavior. That's all we need here for this talk. And if the function is invariant, we call it a modular function. And be quick on this because this was defined in Stefan's talk yesterday. So we want to look at banana integrals. And the first question is, well, what are the actual integrals I need to consider? There's this concept of master integrals, so there's a kind of a basis of integrals that I need for these, all of these integrals, for whatever powers you give to these propagators, for whatever numerator you put. You can always write the result in terms of the integral where you just have the propagators with unit powers and its derivative. And the number of derivatives that you need to consider is equal to the loop number. So if you look at the one loop case, you just need the integral. If you look at two loops, you need two integrals, the integral and its derivative, and so on. And if you put these integrals in a vector, they satisfy a differential equation. It's essentially the same differential equation that Stefan had in his talk yesterday. I just show it here with my convention. So if you put all these integrals, JL in a vector, when you differentiate with respect to Z, you get back the same vector multiplied by a matrix. And it's a matrix of partial functions. And you also get an inhomogeneous term, which would come from the integral that you get when you pinch a propagator, which would be some tadpoles. So you get an inhomogeneous differential equation. So that's a good starting point to try to understand what kind of functions you get at L loops. This general works at every loop order. So how can I solve this differential equation? Well, the first step is to solve the homogeneous equation at epsilon equals 0. And it's known that that equation can be solved in terms of the maximal cuts of the integral. So if I just look at epsilon equal to 0 and I remove the inhomogeneous term, the solution is given by the maximal cuts. And I can take a basis of independent maximal cut contours, call them gamma 1 to gamma L, and put them in the vector, so I get a matrix. So each JL is a vector, and I have the contours label the columns, so I get a matrix W. It's a fundamental solution matrix to this system. What I can do is, well, now, next step, I just divide out this homogeneous solution. So since everything is vector valued and matrix value, dividing out means I do a change of basis. I rotate by this matrix W. And the effect of that will be, well, it will remove the homogeneous term at epsilon equals 0. That's what I had solved. And you see this explicitly that the new differential equation for this vector L will now be order epsilon. I want to point out two things here. The first is that instead of looking at this vector valued or matrix valued equation for the maximal cuts up here, I could also consider a single differential operator of higher order that annihilates my maximal cuts. It's the same. I can always turn a homogeneous system of first order differential equations into a homogeneous higher order differential equation for a single entry. In this case, I take the first entry in the vector, for example. The other thing I want to mention is that if you now want to solve this differential equation in step 2, you have to integrate this equation order by order. That's what we were after. So we have killed the homogeneous term. And so by order, we can integrate it. So order by order, I have to do integrals. And these integrals will now involve this function W, which was the homogeneous solution. And it will involve, well, the inverse of W in particular. And if W is an L by L matrix, this CW here is an L by L matrix, the inverse will contain polynomials up to degree L minus 1 in the entries of the matrix. It's the matrix of cofactors. And also, the inverse and another copy of W. So the first line will give you polynomials of degree L. So you will have naturally integrals to do over polynomials of degree L minus 1 and degree L of the homogeneous equation. And that you can do, and you get iterated integrals. That's how iterated integrals come in the game. So from here, I guess you see now what we want to understand. If you want to understand the kind of functions that we get at higher loops, we need to understand the entries of this matrix W, the homogeneous solution, the matrix of homogeneous solutions. We need to understand their relations, because that's what sits in the integrand, and in particular the integral, the inverse of this matrix, so polynomials of degree L minus 1 if I truncate at first order in epsilon. And that should be the thing that generalizes the formulas that I had for 1, 2, and 3 loops, in particular the modular forms that I had. So that should all come out of here. And the hope will be that if we understand that, we can actually see what is the structure at all loops, and in particular also what is actually coming out for in the Calabi-Yau cases. So to understand that, let's go back to 2 loops. Let's look at what happens at 2 loops. So what do we have at 2 loops? Well, at 2 loops, the geometry behind this picture is the following. The 2-loop banana integral, 2-loop sunrise integral, sometimes called, while I'm looking at the equal case, is associated to a 1-parameter family of elliptic curves. What I mean by that is that for every point z, so z, remember, it's m squared over p squared, and I even allow it to be complex. For every point z, I find the elliptic curve. And I urge you to look, for example, at Stefan's talk yesterday. There was much more details on that. So for every point z, for every kinematic point, I find an elliptic curve. And what is an elliptic curve? Well, I guess you all know, well, many of you know, that's actually, by definition, it's a Riemann surface of genus 1. It's a torus. So over every point z of the Riemann sphere, there's a torus. Maybe degenerate torus. A torus has 2 cycles, and you call it alpha and beta. And the other thing that characterizes a torus, well, it's genus 1, so it has a unique holomorphic differential form. So I have 2 cycles, 2 integration contours, and the differential form, and I can use that. I can integrate my unique differential form, holomorphic differential form over these 2 cycles, and that gives me my 2 periods. And that's something I can use as a way to characterize my elliptic curve. So I can compute these 2 numbers, the 2 periods. Now, since I have this family of elliptic curves, for every value of z, for every kinematic point is the elliptic curve, actually my periods will also depend on z. So my periods will be a function of z. And so I can ask, how do the periods change when I infinitesimally change z? And that is precisely this differential operator that I also got for the sunrise integral. That's this higher order differential operator that annihilates the maximal cuts. And actually, these periods that I get are the maximal cuts. So there are 2 independent maximal cuts for the sunrise integral, and there are 2 periods for my family of elliptic curves. And they're always solutions to this higher order differential operator, which is shown here. Now, you can check, if you look at the details, that this differential operator has 4 singular points, 1, 1 over 9, 0, 1 over 9, 1, and infinity. The 9 here, for example, that would be the threshold. It's the threshold at p squared equals 9m squared. And so it's not surprising that I actually get my periods are multi-valued functions. So my periods are multi-valued functions on, well, so this typos would be CP1 here, it's the Riemann sphere, where I remove these 4 points. And you can actually check that the way there's a way to choose the basis of solutions such that one period is holomorphic at z equals 0, and the other one is a logarithmic sum. That's where you see the multivaluedness. It's this log, for example. The log that in here tells you that if you turn around the origin, this log gets shifted by 2 pi r. This period doesn't change when if you go around 0 because it's holomorphic. Pi b does. But you see that the coefficient of this log is precisely the other period. So pi b gets shifted precisely by A. So if I turn around the origin, my periods are such that pi B goes to a linear combination of pi B and pi A goes to itself. And you can do that for every singular point. You get 3 matrices. They generate a monatomic group of this differential operator. That's what it's called. And you can actually check that the group that you get is a group called gamma 16, which is precisely this group that has appeared, for example, in Stefan's talk yesterday. That is precisely the congruent subgroup for which the modular forms that appear in the banana integral. Well, it's congruent subgroup to which belong these modular forms that appear for the sunrise integral. So is that a coincidence? No, it's not. That is the reason why you get these modular forms for gamma 16 for the two-loop sunrise case. It is because that is the monatomic group of that differential operator that annihilates the maximum cuts. Why? Well, let me define a new variable tau as pi beta over pi alpha. It's the same definition that Stefan had in his talk yesterday. So you take the ratio of the two periods. And you can define this Q, which is again, you can look at Stefan's talk, which was also in there. And I can expand this in Z, and actually you get a holomorphic function. The log disappears. If you look at this Q as a function of Z, it's holomorphic at Z equals 0. And you can even invert it, and now express Z as a function of tau or Q, and it's also holomorphic. So I can interpret this as doing a change of variables from Z to tau. Now, what happens now if I go and literally continue? Well, my function tau, which depends on Z, was the ratio of two periods, but I just showed you what happens to the periods if I literally continue everything. They will change. They become linear combinations. Now also pi alpha changes because it only doesn't change if you go around 0, but if you go around another similar point, also pi alpha changes. So you see that tau will precisely change as a Möbius transformation. That's precisely how this modular transformation is supposed to act. How do they act on this Z of tau? Well, now we know that tau gets transformed as a Möbius transformation. But I'm talking here about analytic continuation. I mean, Z, if I am in a complex Z plane and I move around the complex Z plane, I go along a loop, I can go around any singularity I like, the value of Z doesn't change. There's no cut in there, right? The function Z has no branch cut. So I get back Z of tau. I get back the same thing that I started from. And that's precisely a modular function for gamma 1. So this tells me that this change of variable should precisely be a modular function. While if I look at the period pi alpha, it will, you can easily check from the way pi alpha changes, will precisely become a modular form of weight 1 for gamma 6. So that shows precisely how and why this modular forms and this congruent sub of gamma 6 shows up for the science. It also shows you that it was actually very important to understand this differential operator and understand the periods. The other thing it shows you now is the following. So you can also write this integral over the modular forms. You can write them back in terms of periods. So for example, this H1 here, that is just pi alpha, so it sits outside. H3 we said is at the beginning is an modular form of weight 3, so it's something like pi alpha cube. Pi alpha is a modular form for weight 1, so weight 3 should be a cube of that. And while you also have to change variables from tau to Z, that gives you another pi alpha squared in the denominator, so that again in the integrand you get something that is linear in pi. So you get something that is a period outside and a period inside with an integral in between. If you do it carefully, you have two periods. There's a matrix that connects the two, which is this matrix sigma 2 here. And that's roughly what we expected to get also from the differential equation. So my vector of master integrals should be the matrix of maximal cuts. The maximal cuts we said in the periods. And inside there should be something like an integral over Z, and then something that is related to the periods, and some rational function. So that is this vector. And that's also precisely what we get in one loop. In one loop we had outside this square root, which is the maximal cut. And inside we had the same square root, which is the maximal cut, and the rational function. So that's the structure that you get for these integrals. And that should guide us to what happens for the Calabi-Yaus as well. And as we'll see, it will all generalize in a natural way. So let me wrap up this part. So for two loops, what I want you to remember now for the second part of the talk, where we go to Calabi-Yau, is the following. The maximal cuts of the sunrise, the two-loop sunrise, they correspond to the periods of the elliptic curve. The maximal cuts are annihilated by some differential operator of degree 2, which I call the Picard-Fuchs operator. It has a certain monodromy group, which I can compute, which is gamma 1,6 in this case. I can compute the periods. One of them was holomorphic at z equals 0. The other one had a logarithmic singularity. That's where I get the multivaluedness form. And the general structure of the integral is something that I have a period outside, a period inside, a rational function. So the maximal cuts outside, maximal cuts inside, and a rational function. And then there's this matrix connecting it, which for now, say it's a detail. That's what comes out. If you do the details. And then the fact that I got modular forms of two loops is just because, well, as we explained, if you compute a monodromy group is gamma 1,6, then I can change variables in such a way that all these periods are modular forms. That's why I get modular forms. But that's something specific to two loops and also to three loops, but we will comment on that. But the general structure should be this. It should be about the maximal cuts by periods. Okay, so that is the general structure. So keep that in mind, and let's see how far we can go with that for the bananas. And what I'm going to do now in the next 5-10 minutes, I will give exactly the same talk again. I will replace everywhere the word elliptic by Calabi-Yau, elliptic period by Calabi-Yau period, and it will be exactly the same, almost. So first of all, what is the geometry for the higher loop bananas? Well, the higher loop bananas at L loops equal mass, there will not have a one parameter family of elliptic curves. I will have a one parameter family of Calabi-Yau L-1 folds. But the picture is the same. I have my sphere, which where my variable z lives, which is n squared over p squared, and for each of them, I get the geometry associated with that banana. Now, I haven't told you yet what the Calabi-Yau L-1 fold is. The Calabi-Yau N-1 fold is, well, an n-dimensional manifold with Kähler. Let's forget about it for a second. It's important, but to make the knowledge of elliptic curve, let's forget about it. And it has a unique holomorphic differential form, a unique holomorphic differential n form, which I will call that. It is literally the generalization of my elliptic curve. My elliptic curve was a Riemann surface, in one-dimensional complex manifold with unique, genus 1, unique holomorphic differential form. Now I'm going to do the same, but in n dimensions. I require it as a unique holomorphic differential n form. And so just like for the elliptic curve, I can characterize now my Calabi-Yau with periods. So I have this unique differential for omega. So if I pick a basis of cycles, and that's what I called alpha and beta before, I can integrate my omega over each of these cycles, and I get my periods, my vector of periods. How many of these cycles I have? For the equal mass banana integral, I have exactly the number of loops, which is precisely the number of master cases, which is what we expect. For example, for the elliptic case, which is the case n equals 1, so n here will be L-1. I have two master integrals, I have two cycles. It all lines up. Of course, how can I find these cycles? Well, already in the case of the elliptic curve, I didn't need the cycles in the end. All I cared about was that I had this differential operator, which had degree 2 before, now it will have degree L, that annihilates the maximal cuts. And the maximal cuts will be the periods. So what were before the elliptic periods that corresponded to the maximal cuts of the sunrise will now be the periods of the Calabi-Yau, and they will be the cuts of the L-loop bananas. Now, these differential operators, you can construct them explicitly. This was done, for example, in this paper. In 2 dimensions, you can construct these differential operators that annihilate maximal cuts in 2 dimensions. So you know them, and you can look for solutions. In particular, you can also study the properties of these differential operators. For example, where are the singular points? You can classify them. In 2 loops, this was 0, 1 over 9, 1 infinity. Now it's some more points, but it is what it is. Well, we should add infinity here. These are the singular points at finite distance. And you can also look at what kind of solutions you get. Well, you can also show that independent of the loop order, if you look at the point z equals 0, there will always be one period that is holomorphic, and then you have a tower of logarithmically divergent ones. But just like for the sunrise, they will always be such that the coefficient of the logs will be precisely this first period. It is literally the extension of what we had in the elliptic case, where we had the holomorphic period pi alpha, and the logarithmically divergent one pi beta, and they had stopped. But now you would also have a third period that diverges at log squared, a fourth one that diverges log cube, and so on. Now, such a point is called a MUM point of maximum unipolar. In general, the singular points will not have this property that the solutions look like this. It's only the point z equals 0 that for all loop orders has this structure. The solutions will always look like that. Now, once you know that, you can actually go using something called the Frobenius method. You can go and compute precisely what these periods are. They will in general be new transcendental functions. They will not be logs or elliptic integrals. They will be new transcendental functions. At least that's what you would expect. But there are some new transcendental functions that you can evaluate in a fast and efficient way for all values of z. You have to be careful. You have to initially continue them to all values of the complex plane. All that can be done for every loop order. And so you can, this will be the things that replace the elliptic integrals and the elliptic periods, and you can evaluate. Good, so that's the story for the maximal cuts. What now about the integral itself? So remember what had come out of our two-loop analysis, now our one-loop analysis. We expect something like a period outside, and then a period inside and a rational function. Something of this type should come out. And then there's this matrix in between, because I have L periods, so I have to combine them in a certain way. Of course, now I have to tell the periods we know what we get. We solve compute maximal cuts, we solve this differential equation of degree L. But I need to tell you what is sigma. Well, sigma actually comes from the geometry. Because sigma actually will be this simple matrix with this anti-diagonal with +1, -1, +1, -1. This actually comes again if you go and you look at the monodromy. It must be a matrix that is invariant along the monodromy. So it is given to you by the geometry. It must be this matrix. Whatever you do, it must be this matrix. So then you say, okay, well, that's it. Try this out. Well, you will immediately run into a problem. Because if you compare it to what we had from the differential equation, it doesn't match. It matched the two loops and the one loop, but it doesn't match beyond. Because I have here my matrix of maximal cuts. Well, here's a matrix, here's a vector. That's because here I'm just looking at the first entry of this vector. So this would be the first line of this matrix, which is this. So I have this maximal cuts, and inside I have this inverse of the matrix of maximal cuts. But those are polynomials of degree L minus 1 in the maximal cuts. While here inside I just have something that is linear in the periods. It worked well in the case L equals 2, because then they're polynomials of degree 1, so they are linear. But beyond that, it doesn't seem to work anymore. So my answers that I had that I got from two loops, maybe it's not that easy after. Unless there are relations. Unless these polynomials magically combine and give me something linear. And as we will see, that's exactly what happens. So the reason is, well, consider, for example, this. I take two vectors of periods and I combine them with this matrix sigma. This matrix sigma is invariant. It's monodromy invariant, so this thing makes sense. I can only continue it and it doesn't change. You can show that this is actually equal to this double integral. Remember that the periods pi are obtained by integrating omega. So this is a bilinear in the period, so it's like 2 copies of omega and you do an integral. You have to go through the details, but believe me, this is what it is. Maybe up to some overall factors. And here you can see that this gives you 0, because if you wedge omega with itself, you get 0. And so what you get is actually quadratic relation among cuts. You have more relations. Well, you do. For example, take now the derivative of the matrix of maximal cuts. Remember, the derivative of a master integral is itself a master integral. So this would be the maximal cuts of one master integral, and these are the maximal cuts of another master integral, and then you form this bilinear combination. On the other side, it gives you the same thing. You just need to stick the derivative inside the integrand, and you still get 0. So this would be a quadratic relation among maximal cuts of two different master integrals. Those do not come from IVPs, because IVPs give you linear relations. These are quadratic relations. So where do they come from? Well, here we need to go and look a bit more at the mathematics that underlies this thing. So if you look at the cohomology of Euclid-Labial, it comes with what's called a Hodge filtration. So Hn here, n is the dimension of the space. So this is, if you want, the space of all differential n forms up to total derivatives. And it comes with the filtration. So there's a sequence of subspaces. One subspace sits inside the other like a Russian doll. And what are these subspaces? Well, you should think of them as being, well, Fp is all those differential forms that have at least p holomorphic differentials. So my differential forms, I can, well, I choose my coordinates to be z1, z2, and so on. My differential forms have holomorphic differential forms, anti-holomorphic differential forms, and Fp will be those that have at least p holomorphic ones. And there's a very nice result called Griffith's transversality that tells you if you differentiate this with respect to z now here's my external parameter, my kinematic variable. You take an element from Fp that has at least p holomorphic differentials, so differentiate it with respect to your external kinematic parameter. You get something that lies in Fp minus 1. No, this is highly non-trivial because this is really a statement about cohomology classes, not about differential forms. It's about cohomology classes. So it's as cohomology classes, they're the same. So up to total derivative, you get something that lies in Fp minus 1. This looks mysterious, but it's something that we actually, in the elliptic case, we know very well. Because if you look at the holomorphic differential, that's holomorphic, it lies in F1, that's one holomorphic differential. If you take its derivative, well, this would be an elliptic integral. You differentiate it, you get back the elliptic integral of the first kind, which lies in F1. But you also get something else, the elliptic integral of the second kind. That is the element in F0. So you do not, if you differentiate something from F1, you do not land in F1, you land in F0. Now, with this, we can actually now do the following. So first of all, well, we know that omega, there's Fl minus 1 is exactly just contains omega, because we said there's a unique holomorphic n form. But that means that the next one must at least contain its derivative. The next one must contain at least a second derivative, and so on and so forth. So I get this sequence here, and tells me precisely how, as seen as cohomology classes, the derivatives of omega can be split up into holomorphic and anti-holomorphic components. I insist it's as cohomology classes. With that, I can explain these relations, because the first one we explained, that was omega wedged by itself, an n0 form wedged with an n0 form gives me 0. The next one is an n0 form wedged with a derivative, which lies now, so this is an element in Fn, this is an element in Fn minus 1, so that would be in general an Fn minus 1, 1 form, but that gives me 0, because I cannot, whatever wedge product I take between an n0 form, n minus 1, 1 form, in an n-dimensional complex manifold gives me 0. And that continues like that all the way until I get to, sorry for that, until I get to the highest derivative I can take, because then I get an n0 form which is 0 n form, and that must no longer be 0. And you can actually compute what this term is. And so that's how you get all these quadratic relations. So you get a whole matrix of quadratic relations. You can now differentiate it, you get more. In the end, you see that you get a whole matrix of differential equations, which you can write in this nice form. This, the matrix W is the matrix of maximal cuts. And this matrix will only be rational. That you get it from here, because the C is a rational function, the C that comes out. Now you can ask, are there more? Well, we've searched for other quadratic relations. You can do it numerically by plugging in values and checking if you find quadratic relations. We couldn't find any others. So we conjectured that these are all the relations among the maximal cuts, the quadratic relations among maximal cuts, but it's a conjecture. The other thing that you see now is that if you get this matrix Z, which is rational, is bilinear in the maximal cuts. You can actually turn it around and say that the inverse of W is proportional to W itself in some rational functions, and this matrix sigma, which is constant. So you actually see that the inverse of W is linear in W. But that's precisely what we were looking for. We were looking for something where inside we get something that is linear in the periods. And so we get precisely what we had seen happen at one loop and at two loops. We get the structure where we have the vector of periods outside, this matrix that comes from geometry, and then inside a rational function, which is a very simple one, and again the vector of periods. That's all there is at any loop order. So that is the full closed result at arbitrary loop orders. And since this is actually a very compact, nice and compact formula for all banana integrals in 2 dimensions for any loop order. Now you can say, well, it's not quite true because you need the initial condition. Right? So I gave you, if you want, general solution, but I didn't tell you what the initial condition is. If you go to this paper by Albrecht Clem and this group of last year, they actually give you the initial condition at any loop order. You can write down a generating function now that gives you the initial condition. The way to get this generating function, you need to use techniques of mirror symmetry. I'm not an expert in mirror symmetry, and I therefore ask you to go and look at the paper that they wrote. It's a very nice paper, where you see that the initial condition at large momentum is completely fixed. It's zeta values, and it's given by this generating function. So we have really all the ingredients to write down the all loop formula for the banana integrals. And what I find particularly amazing is that it shows you that it's the very natural generalization of what we had at one loop, where you have the period outside, which is the square root, inside the period, and then the integrals are in between. The next loop order, we had our modular forms. We know now that that's the only thing we can get for the periods outside. So that's the period. Inside, I have my modular form of weight 3. That is because I have this change of variable from z to tau in between. So this formula that we got is the very natural generalization that you can get. It's, in my opinion, it's the simplest way to write down this integral. It's the natural way to write it down that extends what we have seen at 1, 2, and 3 loops. Okay, so we have 2-3 minutes left. So that's just enough to give you some comments about this. So the first comment is I always skip over what's happening at 3 loops, because I said it's modular forms, but yeah. 3 loop is actually special. So let me just briefly tell you why. The geometry here is a Calabi-Yau twofold. It's also known as a K3 surface. It's also one parameter family. The differential operator has degree 3, but it's not some arbitrary degree 3 operator. It is a symmetric square of L2, and L2 is precisely the 2-loop operator. Symmetric square means, well, it's a fancy word, just to say that it's a degree 3 operator, which has a 3-dimensional solution space, but it's written as the product of the solutions from this degree 2 operator. So the 3 solutions that you need are just the solution that you have for L2, the first one squared, the first solution for L2 times the second solution for L2, and the second solution for L2 squared. So these are the pi to 1 and pi to 2 are just what I called before, pi alpha and pi beta. But those we know are modular forms. So that explains why at 3 loops you also get modular forms. But it's really, if you want, it's an artifact of the fact that this L3 is the symmetric square of L2. This will fail if you go to 4 loops, 5 loops, and so on. This is special for 3 loops. So for the last minute, let me just point out 3 questions that I find particularly interesting. The first one is, what about dim-reg? So everything itself was in 2 loops. So if you go to dim-reg, it turns out that you can also write down the differential equations to all loop orders by the same techniques. I'm not going to show you that. But now things become qualitatively and quantitatively different. For example, before now we had this integral that we needed was linear in the periods. Now here you see b tilde, this n to the dot epsilon will be quadratic. So it has a w and a w minus 1. But w minus 1 we know is also linear, so it's quadratic. And more than that, the integrals that you get could even be structurally different. It's, I think, something that would be interesting to understand better, because at two loops, for example, we know that we get the same integrals, the same iterated integral modular forms at 1/6 to all orders in epsilon. This was shown by Stefan Weinzel and Lisa Adams. You just see it from the structure of the differential equation. At three loops, we just argued that in 2 dimensions, you get the same objects. But as we will show in a paper in 2-3 weeks, with Johannes Bull and Nils Mattes, this fails if you go beyond order epsilon. You need something else called meromorphic modular forms. So you can show that these iterated integral of modular forms at 3 loops works in strictly 2 dimensions. Beyond that, it fails. And this theory of iterated integral of meromorphic modular forms, well, it was done for the full modular group SL2Z by Niels earlier this year, where we generalized the whole theory to arbitrary congruent subgroups of genus 0, and we all go through Leggett charm, and you can write down the full answer also at higher orders. The second question is, well, we have now this Calabi-Yau variety. Is that a unique thing? And there we observed something interesting. So for these banana integrals at a certain border, there are actually 2 different Calabi-Yaus that you can attach to it. One is the one that you may naively come up with, which is the one that you get from the Feynman parameter integral. And the other one is some complete intersection construction. So you have a certain number of copies of projective spaces, and you look at intersections in there. For 2 loops, so in the case, they are the same. For higher loops, they are not. You can actually check that these 2 things have different Euler characteristics. And the one that is more convenient for calculations is actually the second one. It's not the first one. However, they define the same motive. I'm not going to define what the motive is, but there is a sense in which these things are the same, but it's not a geometric object. It's not a set of points. And the last thing is that which integrals can actually be attached to Calabi-Yau? Well, the naive answer would be not all of them, because we know that the Feynman integrals that give rise, well, when you look at the maximal cuts, gives you the opposite of genus greater 1. Riemann surface of genus greater 1, meaning there's more than one holomorphic differential form. So that's precisely what Calabi-Yau varieties should have, one holomorphic differential form. So these geometric objects that you get there are definitely not Calabi-Yau varieties. But at the same time, it is known that there are Calabi-Yau motifs that describe Riemann surfaces of higher genus. So just like before, we had these 2 varieties that actually correspond to the same motif. There's also still the possibility that these higher genus objects that have been observed could come from Calabi-Yau motifs. So at this point, it's not even excluded that all Feynman integrals could come from Calabi-Yau motifs. Don't have arguments in favor nor against. I think that would be a very interesting point to investigate for the future. Okay, I think I should stop. So I hope I could give you a glimpse of what Calabi-Yau varieties are from the Feynman integral perspective, and that they're interesting and they're the next frontier. And that they are maybe not be as scary as we may have thought that they are, because many of the things that we know from 1 loop, 2 loop, 3 loops actually generalize, and you get, in this case, the banana integrals, which admittedly are a bit of toy examples, you get just closed formulas that work for every loop order once in a standard geometry. And I think this gives hope that we can even understand things more precisely for these more complicated geometries. But I think that's a story for future research. So for the moment, I just thank you for your attention.
Thank you very much, Claude. Beautiful talk. So let us all unmute and clap, and then there is time for questions. Okay, so the stage is open for questions for Claude. Who wants to start? Maybe Lance.
Hey, Claude, thanks for a nice talk. In Stefan Weinzierl's talk, he was talking about using modular transformations to move to a part where a modulus is very small for numerical reasons, and that he had to track, I guess, how the fibers transform. What would you say about the analog of that in your setup?
Okay, so it's a very good question, very relevant one. So let me go maybe back to here. So it's related, if you want, to this comment here. So these modular transformations where you expand in this Q series, well, if you have an elliptic family, well, definitely for the banana, I think is actually true in general, the singularities will all be mum points. And this means that you will always have this Q series expansion close to them. In general, you could get such an expansion close to every singular point, close to every point even. Right? So if you want, I could go these expansions that I get, whoops, where is it here? Yeah. So I can write Z in terms of SQ and then plug it into, so if it is elliptic, I can write Z as Q and plug it in here and I get these Q expansions. Now, doing these modular transformations to expand around another point is like doing the expansion in Z around one of these other singular points. And then plugging in again what Z is as a function of Q. That is what these transformations are. So the closest you would get here for those things is then the expansion of these objects close to other singular points, which you can always get from the differential equation. That's actually how we evaluate them. You get series expansions close to every singular point, and in this way you cover the whole real line, for example. What will fail is that not all of these singular points at higher loops will be such mum points. And so you won't have Q expansions close to every one of these points. But you will always have the expansion in Z, which is fast conversion.
So if you landed near one of those, if you needed a point near one of those other points, it would be more difficult to evaluate it numerically. Is that what you're saying?
No, you just have, you wouldn't get Q expansions. You would have close to every singular point you have.
Okay, you'd have another series expansion, but it'd have a different nature to it.
Exactly.
Okay.
Would have square roots, for example, in it.
But it might, in a multivariate case, it might still be a big challenge to map out where,
And
okay.
This for all values of Z, we could do it efficient for all values of Z, could do it in the equal mass case. In the different mass case, if you have 4 loops, for example, you have 5 variables, it's a nightmare.
Yeah. Thanks a lot.
Okay, I think Lorenzo was next. Please, Lorenzo.
Yeah, hi, Claude. Sorry, this is probably a triviality that I just failed to catch. But when you were moving from the elliptic case to the Calabi-Yau case, you were using this language of periods, which on a torus we know what they are because there are only 1 cycles. But here we are considering, as I understand, higher dimensional objects. So in principle, there are higher dimensional homology group as well. So you could consider periods defined as integrals on surfaces that wrap around the Calabi-Yau, for example, S2s. Do these play any role?
Well, here, of course, there are other homology groups. There are also other differentials. Here, what I'm saying is have a unique, distinguished holomorphic differential n form. It's an n0 form. That's unique. So there's a unique n form. So if I choose a basis of independent n cycles, which probably have said here n cycles.
Okay.
Then I get this basis of periods. Of course, if I now look at other cohomological dimensions, I could look at 1 forms, 2 forms, whatever, or I look at even other, I mean, just like the elliptic curve, I also have my meromorphic differentials, the differential of the second kind. I can build other things. But just like for the elliptic curve, I have a distinguished unique differential, and then I use all cycles that I can and integrate over it, and that gives me my set of periods.
Yeah, so it's n cycles within this. Okay, thanks.
Yeah.
Okay, next question, Matthias, please.
Thanks, Claude, for the fascinating talk. So I was wondering, how does this story change if you're going to the unequal mass case that you mentioned before?
So for the unequal mass case, this story is exactly the same, what you see here. Essentially, this is all the same, but of course will change is this. But you can still write down something like this, but it's a bit connected to what Lance asked, what do you do in the multi-parameter case? It's a bit also what already happens for the elliptic case. So there, already at two loops, you don't have a representation in terms of iterated integrals of modular forms in the different mass case. It's something specific to the equal mass case. So now you can speculate that this should give you something like Calabi-Yau polylogarithm, but I think we are far from that. So there, right now, the best you can do is then go, for example, either you go back to the differential equations or you do it from some kind of iterated integral representation like that, and you get series representation again close to every point, and you can evaluate them. So you can evaluate it. That we can do, but with the caveat that Lance already mentioned, if in the multi-dimensional case, getting all of the branch cuts right and getting it fast and numerically convergent in the whole multi-dimensional parameter space can be a challenge. But you can get series expansions there that converge. But I wouldn't know what is the kind of class of iterated integrals that I would write down, because I wouldn't know what is the equivalent from going from iterated integral modular forms to elliptic polylogs. I don't know what the equivalent of that is if you're in the Calabi-Yau case.
Thank you.
Okay, next, Andre.
Thanks for the talk. Yeah, I was just curious about because I think you've given us some detail how you construct the homogeneous part of these functions, and then you have this inhomogeneous integral, which in the case of the bananas is not too complicated, I would think. But what kind of general functions do you expect that to evaluate to? Is it always going to be something like if you're working at Calabi-Yau, L-1 fold, is it going to be L-2 or?
So sorry, maybe, so the first question was about constructing, how you construct these solutions, is that it?
Well, I was just saying, I think you've explained how you do this.
Okay.
And the last piece of information you need is to integrate over this inhomogeneous term.
Yeah, so that's what gives you this, right?
Yeah. So I was just wondering, are these inhomogeneous integrals?
Oh, but these are literally the subtopologies, right? So
they are literally the subtopologies. That's what I was wondering. Yeah. Okay.
Which, admittedly, for the bananas is particularly simple.
Yeah, exactly. I was just curious on more general cases. You would just see functions you already know, so it's not so bad.
Right. You see whatever you see in the subtopologies.
Yeah. Okay. Thanks.
I see that we have a question from David next, please, David.
Yes, thank you for this wonderful talk. It's very satisfying to see how much mathematics is accessed just in or near 2 dimensions. I want to make a comment on your answer to Lance, which is perfect. I agree with everything that you said about numerical evaluations when one doesn't have modularity. But it really is extraordinary what modularity gives you in the 2 and 3 loop equal mass cases, because the transformation between singular points is just an Atkin-Lehner transformation on gamma 0, 6, which just turns one eta quotient into another. So that when you know the expansion about one point, you can find the expansion about the other point and achieve that efficiency that Stefan was talking about. When you go to 4 loops, and I had to get to quite high numerical accuracy at 4 points to identify the quasi-periods of the modular forms of weight 14 and 34, which have been identified by the Oxford group of Ossia. Then I really had to struggle quite hard to do it. You're essentially expanding about some point, getting to some place where you know things of that convergence, and then positing an expansion about another point and fixing your constants. So whilst we can achieve those accuracies, it's nothing like the lightning efficiency of modularity in the 2 and 3 loop cases.
Yes, I agree. Of course, one should also, the question is also what one wants to achieve. But say if for applications you want 16 digits that is a different goal than if one wants, I don't know, a couple of hundred digits, for example.
Yes, but what the mathematicians wanted was an exact formula, which I was able to
Yeah.
find from PSLQ at 10,000 digits.
Yeah. So that then, yes, that is a different game. I fully agree.
Okay, so I think at this point we are getting into the dinner break. So let us all thank Claude again